Good afternoon, everybody. This is Marco from ETA Florence, and on behalf of IEA Bioenergy, I'm glad to welcome you to this webinar titled Integrated Biogas Systems, Sustainable Solutions Beyond Energy. The webinar will be moderated by Jan Libetro, will feature presentations by Jerry Murphy, Jan Sannenberg, and Marcus Gustafsson, and will feature also a panel discussion with the participation of Mats Eklund, Stefan Anderberg, and Karian Ling. I kindly remind you to use the Q&A tab for questions addressed to the speakers, so they have the chance to answer directly there, or to include the questions in the final discussion. And Jan, the floor is yours.
Thank you very much, Marco, and of course, thank you very much also to ETA Florence for organizing this webinar. I would like to welcome you to this webinar of IEA Bioenergy. And we would like to discuss today integrated biogas systems as sustainable solutions beyond energy. You might know as well that anaerobic digestion technology is around for more than 100 years now. It has mainly been used in the past as a treatment for wastewater and solid waste. But coming up in the two last decades, we have seen a lot of installations of biogas systems. And this is due to the growing demand for renewable energy and, of course, in particular for renewable gas. The REPowerEU plan has now set very ambitious targets for biogas systems, but this has also led to discussions around the technology. And that's why the members of IEA Bioenergy Task 37 have been developing a position paper to present our views on the main aspects of the biogas systems. And I would like to start the webinar today here with highlighting some main aspects of this position paper. The position paper will be published right within this webinar, so you can find the link in the chat section if you are interested to look at it. The pathway to net zero requires far more than the mere precision of renewable electricity. I think this has been clear, maybe not from the very beginning, but in the last years, this gained more and more discussion. And we need, of course, also renewable gases and liquids for a net zero economy. Biomethane and biogas and biomethane solutions have the big advantage in that context that they can feed directly into an existing gas infrastructure. And this path provides the least resistance to decarbonize natural gas applications. Since biomethane is a direct substitute of natural gas, all the infrastructure and also the utilization pathways are accessible for this renewable gas. On the other hand, biogas systems have even an advantage because they contribute to the energy security, since the whole production chain can be set up locally and also operated decentrally. So we have the whole system under control. Biogas production is based on anaerobic digestion, and this process can utilize a wide variety of organic feedstocks. To start with waste material, waste waters, then moving on to residues from industrial processes, but also from agricultural processes. Industry, food and beverage industry, paper industry are large producers of residues which can be used in anaerobic digestion. Agricultural residues as manure and straw are already in many applications to be found. And last but not least, we can also use plant material as cover crops or intermediate crops, catch crops in biogas plants. Biogas plants do not only produce the gas, the energy carrier, they also have a byproduct, it's the digestate, and this can be used and applied on agricultural land. and actually substitute artificial fertilizer. There are a lot of externalities coming with biogas. This adds to the multifunctionality. So biogas solutions can reduce fugitive methane emissions from waste, from manure, for instance. By doing so, by treating the waste, they protect anaerobic digestion plants, protect water qualities. They reduce pathogens in waste materials, in manures. They can be used as fertilizers, as already mentioned. They reduce odors. They improve air qualities, for instance, by use as fuel, biomethane utilization as fuel. And last but not least, the application of the digestate also improves the soil quality. When looking at biogas solutions, one should be aware of the fact that they are all geographically and politically bespoke. So they have a very individual implementation. They have a very individual technical components. The best solution in one region is not always the optimal to another region. So whenever developing a strategy, whenever developing an overall plan to develop the sector, we need a regional assessment of the situation. And this should include, of course, the availability of substrates, the costs, the impact of the specific feedstock utilization. Some of the feedstocks which I named, they interact with other applications, with other already existing uses of these feedstocks. And this all should be paid attention into in a detailed analysis and a strategic plan for the development of the sector. One aspect which is gaining more and more importance is the use of the CO2 within anaerobic digestion processes. We have a gas which contains already large fractions of CO2, and biomethane provision produce an almost clean byproduct, the CO2. And this CO2 can be used in carbon capture and storage or in carbon capture and utilization. Further use of the CO2 could be biomethanation, thus would lead to a large increase of the biomethane provided. A very important aspect is the economics of the process. First of all, when doing and comparing biomethane with other technologies, make sure that you compare like with like. We should compare biomethane to other renewable gases and not to fossils. This is a very important aspect. And when we are comparing biomethane with renewable gases, then there are not so many options when we talk here about hydrogen or synthetic methane. At the moment, we can state that biomethane is cheaper than the green hydrogen. And this is also expected to remain for some time in the future. We have the infrastructure, which I already mentioned for biomethane. This is other than for hydrogen. However, we do not see biomethane or hydrogen as competitors. We see them as an addition to the overall plan of a net zero economy. And in a framework, an overall economic framework, which includes, of course, the costs for CO2 reduction and which includes also externalities of these processes, then we can see how the development will look like and which technology might be the optimum use in all the different applications which have to be driven by renewable gases. The externalities of biogas process, which I already mentioned, they could be assigned in an economic value. However, we don't see that this will be in the near future the case, but they should be considered in multi-criteria assessment in order to make decisions for developing and supporting technologies. So this is something which will be presented by Jonas later here. Any incentive for the deployment of biogas systems should reflect actual costs. They should provide long-term stable conditions in order to attract investors. to attract bankability. We need removal of regulatory barriers on the technical and also on the administrative side. And as I already mentioned, an overall framework, maybe including a carbon tax, which kind of makes renewable products compatible to fossil products, is the only chance to remove the incentive systems in the future, because then we balance out the cost advantage which fossils have at the moment, because they are not considering the CO2 price. Summing up, biomethane biogas have a relevant role in a pathway to net zero. We will need renewable hydrocarbons, and biogas and biomethane are required hydrocarbons and also cheap CO2 supply for a future net zero economy. And they have plenty of options and utilization pathways, which make them very flexible for future utilizations, and also very flexible within this changing system, which we expect to see within the next 20, 30 years. The position paper is, as I already mentioned, is available on our website. As said, it will be in the chat, so I'm inviting you to have a look on it. And if you have questions, or if you would like to comment on it, you are welcome to give a feedback also to IEA Task 37. So now I would like to start with handing over to the actual presentation we will see here today. We have based our selection here on the work of IEA Bioenergy on the one side, and of course also on current development and discussions we see in the sector at the moment. In particular, the program is based on a technical report which has been published by IEA Task 37, IEA Bioenergy Task 37, which is named Perspective on Biomethane as a Transport Fuel within Circular Economy, Energy, Environmental Systems. And we have 5 of the authors of this report available here today. We will start with 3 presentations given by Jerry Murphy, Jonas Ammenberg, and Marcus Gustafsson. And then we will follow up with a panel discussion, including Mats Eklund and Stefan Anderberg and Karian Wing, which are also available to answer your questions. As already mentioned, feel free to type in your questions in the Q&A section that we can answer them during the panel discussion. And for now, I will stop talking and I hand over the screen to Jerry Murphy. And Jerry, we are looking forward to your presentation.
Thank you, Jan. Thank you for that introduction. You might let me know when hopefully you can see my screen.
I can see your screen.
And is it the slideshow?
It's the slideshow, and I can hear you clearly.
That's great. So I'll start, Jan. Thank you. So my name is Jerry Murphy, and I'd like to talk about biogas systems and circular economy, energy and environmental systems. I serve as the director of the MCA Centre here in Ireland. We have about 250 researchers, and I work with Task 37. I led the task for 6 years, but I passed over to better hands in Jan. Within our research group, we sort of work off this canvas. So we have this circular economy, energy, environment, hard to abate sectors. And I hope over the next 15 minutes, I'll show how this links together. So we look at linking the gas system with the electricity system, with the water system, and we're looking for serendipity and environmental improvement. So if I start on the bottom left and look at anaerobic digestion, within the International Energy Agency, TCP and bioenergy, we have this website with lots of case stories, which are around 4 pages in length, and technical reports, which are about 40 pages in length. And we look at making them available for a general audience as opposed to peer review journal deep papers. One of our reports looks at the role of anaerobic digestion in the circular economy, and it's something we feel is quite important. You do not build a biogas plant for the same reason you put up a wind turbine or a PV array. It needs to fit into an existing system. It needs to work on typically byproducts, environmental improvement, so we can take slurries and digest them, food waste, processing industry waste. We produce biogas, which can be used for electricity, for heat, for injection into the gas grid as a transport fuel. So it's a complex system, which can make it difficult to explain and to synthesize. This is a case story I really like. It's an organic farm in Denmark. And when you go organic, you do not have fertilizer, you do not have weed killer. They actually have a tractor where they pull people along to pick up the weeds. So there's no chemicals or outside elements brought into the farm. The yields of the crop decrease. So by taking manures, digesting them, mineralizing them, making the fertilizer, the ammonia available, we have growth coming back. So we built this biogas plant to produce biofertilizer, but the end product was that the milk from this organic farm was assessed as greenhouse gas negative on a whole life cycle basis. These are our partners in Brazil. They have a lovely campus, lots of grassland. Grass cuttings were a problem. They now power cars. So 60 cars are fueled from grass cuttings in parkland. We look at the logistics because there's always problems, but our perspective is you can always overcome a problem. And this is where biogas systems are very, very bespoke. They're one-off solutions that are applicable for specific geographical areas. So in this system, there was a number of small biogas plants, and to upgrade that biogas to biomethane and employ economies of scale, they piped the biogas. So biogas was piped over distances to a hub, and the hub upgraded that biogas to biomethane for a transport fuel, and also liquefied CO2, which is a product. And then alternatively, in this situation, instead of piping biogas, we pipe slurry. So in Denmark, they have this policy of not spreading slurry on the land, having 6 months storage, grant aided to build these large storage systems, probably more economical to turn them into a biogas plant. So the farmer drives to a hub, drops in the slurry, it's augered to the biogas plant, and the biodigestate is augered back. So we have two very contrasting situations, piping biogas or piping slurry. So there's always solutions. We've looked at Ireland, where I come from, and we've looked at the large energy users, and we looked at the gas grid. And we did find, for example, a number of the large energy users were off the gas grid. So what we looked at is drawing a 2.5 kilometer circle around, for example, a large creamery, and digesting slurries and dungs and surplus grass. We found we could cover the gas demand of these industries in a local setting. So again, another solution to a problem that is bespoke. When we look at industry, we can decarbonize the production of alcohol. So this is a brewery in Austria. They're now decarbonized. About 50% came from biogas, and the rest came from wood chips and PV. So it was an integrated solution, including for biogas. Another area that's quite nice is CO2, and CO2 is a product. I have a lab, I use CO2, hospitals use CO2, meat processing plants use CO2. In Denmark, the market is 65,000 tons of CO2. This biogas plant segregates CO2 from the biogas, methane goes in the grid, the CO2 is processed and is sold as a food-grade CO2 product. This, to me, is an important element of the whole system. Open slurry tanks emit methane to the atmosphere. Typically, 18% of the methane content is emitted in the slurry tank, goes to the atmosphere, global warming potential of 28 over a 100-year time frame. If you cover that slurry tank and make it a digester, you can limit the slippage to 2%. So in essence, we can have a greenhouse gas negative fuel on a whole life cycle basis. So if we take that methane and go to the heart of the debate sector of a coach or a truck, we're reducing CO2, which is 28 times less global warming potential than the methane. And we're coming out at minus 250 grams CO2 per megajoule. Quite interesting, this is a co-op in Switzerland, small renewable energy systems, PV, hydroelectricity, wind power, and a biogas system. But the biogas was very useful in that, number one, it's dispatchable, but number two, it can be ramped up and ramped down depending on how you feed the system. So in this case, biogas allowed to plot the day-ahead market when the wind wasn't blowing, at nighttime when the PV wasn't working. So it's a flexible component in renewable energy production. And we've done a lot of work within our own research group in plotting such systems. So we can figure out how to plot the day-ahead market through pulse feeding, through storage. So then I want to look a little bit, I want to jump a little bit, but it comes back. Hydrogen, there's an awful lot of interest in hydrogen. And we see this as a complementary renewable gas to methane. If I bring you to Ireland, which is interesting because we are an island grid. We don't have the huge interconnection that might be available in mainland Europe or in America. We just built an interconnector to France. It's a 0.75 gigawatt. It's a huge investment for Ireland, but it's 0.75 of a gigawatt. Ireland has a capacity of 8 gigawatts at the moment. We have 40% renewable electricity. And at this, we've reached the highest level of system non-synchronous penetration. So our electricity grid has had the highest amount of variable renewable electricity on it at any one time compared to any other electricity grid. We've actually spent 150 million euros on a wheel that turns around to provide inertia to our grid. And for 2030, we're looking at 7 gigawatts. We're looking at 2 gigawatts of hydrogen, and the Dublin Declaration is 260 gigawatts. So the idea is we will vastly overproduce electricity so we can provide for the electricity market and have more hydrogen. When we look at Ireland at 2020, we are spilling 12% of our electricity because we can't use it. It's being produced at a time when summer nights we're in bed, windy, we spill that electricity. So there is this concept of producing electricity and hydrogen from offshore wind. When we look at the costs, and cost is interesting because typically biomethane is probably 3 to 9 cents a kilowatt hour. If we have offshore wind at 4 cents a kilowatt hour, it'll produce hydrogen at 11 cents a kilowatt hour. And if you go back to electricity from that hydrogen, it's 18 cents a kilowatt hour. So wind to hydrogen to electricity increases the cost of electricity by a factor of 4. And hydrogen at the moment will be more expensive than biomethane. We do see great potential in transport. Putting hydrogen into a fuel cell is equivalent to about €1 per litre diesel equivalent. So what we have been looking at is the idea of mixing the hydrogen and the biogas system. And we visited Wörtel in the north of Germany. There is a food waste digester. It puts methane in the gas grid. CO2 is left behind. They have a 6 megawatt electrolyzer making hydrogen from electricity. And they react the hydrogen with the carbon dioxide to make methane. And that's a Sabatier process. It's a chemical process operated at about 400 degrees Celsius. So we're bioengineers, and what we did is we went back to the lab and we started mixing hydrogen and carbon dioxide in a microbial broth, and we found this Methanothermobacter wolffi who eats hydrogen and carbon dioxide and makes methane, and does it at about a 95% efficiency. So we looked at strategies for ex situ biomethanation. Hydrogen is not very soluble, so we needed a recycle of the hydrogen. In a continuous process, we needed a number of systems. So we modeled this system and then we built it in the lab. So we have our 3 reactors and our gas goes into reactor 1. goes into circulation, reactor 2 into circulation, reactor 3 into circulation. And we found that in the third reactor, we were at over 97% conversion efficiency. And we call this ex situ biomethanation, and others are working on these systems also. So we can capture hydrogen and carbon dioxide and make methane. We call this power to X. And in this case, X is methane, but we can go on to methanol, we can go on to Fischer-Tropsch. So we're then looking at applications. And one of the things we looked at is if we put an electrolyzer on a wastewater treatment plant, and in Cork, where I live, we have a 420,000 person equivalent plant. So we sized this plant based on the oxygen demand. So the electrolyzer would be sized on the oxygen. It ended up being a 10 megawatt electrolyzer. It was equivalent to the curtailment of 18 8 megawatt turbines. Roughly 30% of the methane was required to upgrade the biogas to pure methane, and 70% of the hydrogen was left behind for other uses. So we're looking at valorizing oxygen, upgrading biogas to pure methane, and having hydrogen for other uses. And in this case, we could power roughly 400 trucks on the biomethane and on the hydrogen. And we found a plant in Copenhagen, the Biogas plant, and in this, they produce 125 meters cubed of biogas, 50 meters cubed of CO2. We need 200 meters cubed of hydrogen from 1 megawatt of electrical power. All the CO2 becomes methane. So we now have 125 meters cubed of biomethane when we only had 75. So we've increased the resource and upgraded the biogas. And this leads to the potential for every digester that was ever built could have an electrolyzer next to it and an ex situ biomethanation as an upgrading system. And it also leads to national plans. So in Denmark, at the moment, 25% of natural gas is substituted by biomethane. They have a plan to be fully decarbonized by 2035. That's 72 petajoules of biomethane. However, by bringing hydrogen to these biogas plants, they could increase the yield to 100 petajoules. So the power to X would upgrade the biogas to methane and increase the yield and make the resource of methane far bigger than it is. One thing I wanted to look at is biorefinery type systems. And this is one example. We looked at a carbonate bicarbonate cycle. So our biogas goes into a tower, it goes into solution. Microalgae also go into the tower and they take out the CO2 for cultivation. So it's a carbonate bicarbonate cycle. We ran it in our laboratory. It works. We can get 99% methane and we grow microalgae. And this is of interest because in the Climate Action Plan in Ireland, they talk about the marginal abatement cost. That's the cost to remove a ton of CO2. In Ireland, the cost was €300 a ton in this study. It was positive. So therefore, it was a very poor technology from an economic perspective, according to this report. Like, we would disagree with this in that when we looked at the marginal abatement cost of a food biofertilizer energy system, so those emissions go to the food, which is a vegan food, microalgae, the biofertilizer, and we have a number of scenarios as we're academics, but they're all negative. So our perspective is the marginal abatement cost of biomethane is not positive, it is negative in a proper circular economy system. The last thing I want to look at is the end uses. We did a study on a very large distillery. We looked at 21 decarbonization pathways. We could electrify and have some level of decarbonization. It would be the cheapest decarbonization, but to get over 65% reduction in greenhouse gas emissions, we had to digest the byproducts. And we are looking here at scope 3 emissions where the biofertilizer goes on the land. The trucks are running on biomethane, which is a scope 3 emission, and the scope 1 emissions reducing natural gas combustion at the facility. This is a lovely report that I worked on with my good friends. It'll be presented by Jonas. It's the perspectives on biomethane as a transport fuel within the circular economy, energy, environmental system. And in all these systems, we're starting with byproducts, with industry, we're looking at serendipity, we're looking at circular economy, but we end up fueling coaches and trucks. A last thing, methanol, and this is where we go power to X. If you look at methane, it's CH4. Methanol is CH3OH. We're adding an oxygen. And it's very easy to go from biogas to methanol. And methanol will be the decarbonization fuel for shipping. So when we look at the hard to abate sectors of shipping, of trucks, of coaches, there's a huge advantage to methane, to power to X, and to methanol. These are some of my colleagues in MRI. That's my presentation finished. I'll thank you very, very much. Thank you for asking me to present here. And I'll pass you over to Jonas. Thank you.
Yeah, thank you very much, Jerry, for keeping the time and of course for this very, very interesting presentation. So now the next presentation will be given by Jonas Ammenberg, and he is with the Environmental Technology and Management Center of the Linköping University. And he will talk about the multi-criteria analysis, which we think is a very important tool to really assess all the externalities coming with biogas technologies. So we're looking forward to your presentation, Jonas.
Thank you very much, Jan, and you can see my presentation, I hope.
Yes, I can see it, and I also can hear you.
Great. So hello, everyone. I really appreciate this opportunity to present here. I'm Jonas Ammenberg, Associate Professor from Linköping University, as Jan said. I also represent, together with some colleagues here, the Swedish National Biogas Solutions Research Center. Yeah, I will talk about multi-criteria analysis of biogas solutions and complementing technologies, comprehensive assessments for more informed decision-making. First, a few words about this Biogas Solutions Research Center, or BSRC. And it's a center where we co-produce knowledge with about 50 participating biogas actors. We are 10 research groups from Linköping University and the Swedish University of Agricultural Sciences. And it's supported by the Swedish Energy Agency. And we try to have a real broad transdisciplinary approach. So the center is not only dealing with AD processes or technology, we actually look at societal conditions like policy that Marcus will soon talk about, the production systems like economics, LCAs and stuff, use and markets, and the broader societal sustainability effects. We do this together with biogas producers, large and small, technology providers, can be those providing technology to biogas plants for upgrading and liquefaction. We also have, for example, Scania producing vehicles like coaches or trucks. We have large biogas users like industries or organizations dealing with shipping. We have representatives from the agriculture and horticulture sector and different types of public organizations like county organizations, municipalities, sector organizations. And I would like to emphasize that quite a lot of what I will talk about today can be said to be based on a Swedish or maybe even Nordic biogas model. And what do I mean then? Well, first of all, to a large extent, the biogas is produced from different types of wastes or residues. So it can be food waste, it can be industrial bio-waste or slaughterhouse waste, it can be sludge from wastewater treatment plants, it can be agricultural residues and manure. And the raw biogas is to a large extent upgraded and used for transport. And the digestate is largely used as a biofertilizer in the agricultural sector. And of course, we are also looking at what can be done with the CO2 that is separated in the upgrading phase. And the title of the webinar says Beyond Energy, and you got many examples already, but I will also try to emphasize that this Biogas Solutions and especially the Nordic biogas model is about much more than energy, as you maybe already see. I will talk about multi-criteria analysis, MCA. Sometimes you also see multi-criteria assessment, which is similar, and you also have the area of multi-criteria decision making, and I will not separate them today. The background here is that, at least according to me, many views and important decisions are based on very narrow perspectives. So you could refer to a kind of silo mentality sometimes when it comes to important decisions relating to energy or transport or agriculture, not least regarding policy and so on. And it's much more than energy. So as was stated before, it's not wise to really like compare a biogas solution to like a monofunctional system as a wind turbine or a nuclear power plant really designed only to produce electricity. And commonly you should have much broader perspectives than just focusing on tailpipe emissions or engine efficiency. And of course, climate impact is really essential, and the biogas solutions can have very competitive climate performance, but there can also be many other impact categories of relevance to include, and sustainability categories. And when it comes to MCA, another important point is that we want to go beyond quantification. Because if you look at the different systems that, for example, Jerry showed, there are many different types of effects and values, and we cannot, in a good way, quantify all of these values. For example, there are important limits to monetization. So the idea here is to have a much more pluralistic approach, to have several indicators and work with several units, not just one. And for all system studies, like the ones I'm going to talk about today, it's very important to focus on what's included, for example, in a product's life cycle or in the society. What impact categories are we focusing on, and what time perspective? Are we assessing the current system or the system we will have in maybe 2050 or so? So I would say that the MCA context is very much about learning, also for us as researchers, but stakeholders and even experts can learn a lot from conducting a multi-criteria analysis study. So they are commonly used as decision support methods to make more informed decisions. It's commonly the case that we have a lot of different alternatives, at least a few, that we want to compare. For example, we want to compare their sustainability performance. We want to highlight strengths and weaknesses can be related to sustainability impacts, risks, their efficiency. You can also use MTA to study how to improve different systems or products. And commonly you apply them when you have a very complex system or a complex problem, even a wicked problem it can be called, because there is no obvious or simple solution. It's not obvious what alternative is best. It very much depends on what you focus on. And the choices make will commonly influence various types of effects. So you need a transdisciplinary approach to deal with these kind of problems. So at least I see it very much as a tool to manage essential information. And a lot of that information might already be available somewhere. But the job, for example, of researchers then is to select the most relevant information and to structure it. And that facilitates a lot for those that are going to take an important decision. And then I mean both quantitative and qualitative information. It's also common that MCA is used as an overarching method, making use of results, for example, from life cycle analysis, life cycle costing, lab studies, or whatever. And we also conduct these kind of studies, of course. But today I'm focusing on multi-criteria analysis. Going back to this Swedish or Nordic model, some colleagues, Ruspe Face, Mats Eklund and others have been considering what if we would, for example, take the systems we have in Linköping, shown at this picture, and export them to a million city, maybe in a country that is a little bit less developed. So you have more traditional solutions for waste management, transport, treatment of wastewater, and so on. What effects could we get then? And then these effects are categorized into 4 categories, those relating to transport and energy, nutrients and soils, resource and waste management, and some broader effects. And we have limited time here, so we can just look at a few of them. Of course, you will then improve your energy supply. You will have a more renewable energy system. You will improve recycling, have more circular solutions. You might free land that can be used for buildings or so on instead of for landfilling. You can have more sustainable nutrient management, improve your soil fertility, as was mentioned by Jan, for example, and this can really facilitate for ecological farmers, as Jerry mentioned. And the 4th category is very broad, ranging from like climate improvements to more green jobs to improved competitiveness for local and regional companies. To provide some examples. I also included this picture because in many contexts we say that we need or we want a more bio-based and circular economy. And then an important organization that has done a lot of work here is the Ellen McCarter Foundation. And I find it interesting that in this picture that is commonly used from Ellen McCarter Foundation, you really see one technology clearly. And we find the biogas solutions here because they are very essential if we want to have more circular nutrient flows and more renewable energy, I assume. Looking at the MCA process more in detail, you commonly see 5 steps. First, you define the goal or the problem. Then you look at, okay, what alternatives to assess. You establish the method. For example, there can be indicators matching what's relevant to compare. Can be just a few, or there are examples of up to hundreds of indicators. You collect data for these indicators and each alternative and assess them, and you interpret the results. And this may look a bit linear, but commonly I would say it's a very iterative process, and it can also be literature-based in combination with a participatory process. So you can have stakeholders and experts involved in establishing the method and also in the assessment. And of course, you can choose to aggregate a lot of results here as well and come up with one answer. But we at least commonly stop with results for each indicator, and we don't see it as the task of researchers to do the weighing, so to speak. Time is running out, but I will give you a few examples. We have conducted MCA studies for the last decade, which are relevant for Biogas Solutions. So I will show you a few examples so you can see some types of methods, maybe get an idea of how they may look like, and also how the results may look like. And then I will draw some general conclusions that can be discussed maybe later on. So we have used multi-criteria analysis to look at different types of feedstock for biogas, to look at vehicles like buses and trucks. We have used these kind of methods to compare different developments within biorefineries. And we have ongoing projects where, for example, Marcus is involved, where we look at how you can use the CO2 from biogas production. So I will start with a dense table related to the feedstock problem. What feedstock is most suitable for biogas? And we can't go into the details at all, but you see that in this case, we have many indicators, 17, ranging from like biomethane yield to nutrient content to how much you can produce totally, technological feasibility, environmental indicators, and so on. And already now, it should be emphasized that the sustainability performance of biogas solutions is strongly linked to what feedstock you use and the systems behind that feedstock. For each indicator, you need to define each indicator and have a scale for assessment. So commonly we have used 5 levels. So you can see that you can get results from a very poor level to a very good level. And in this case, regarding biomethane yield, it was a quantitative scale. And I will provide another example just to show you a more qualitative version. So regarding suitability for anaerobic digestion, we have the 5 levels, and here it's more text-based. And if you end up here, it's very hard to digest the feedstock. If you're up here, it's quite simple. You can even mono-digest it. And you can present the results in many different ways, of course. Here you see just a limited share of them. So you see a few of the indicators. You see some feedstocks. And if it's, for example, dark green, it means that it's a good situation for that feedstock in relation to that indicator. And 3 stars mean that we are pretty sure about this result. If it's red, it could be a job stopper. In this case, I think it's quite easy. You can just co-digest with something that is better from a nutrient perspective. If it's 1 star, it means that we are more uncertain. So for example, regarding farm blue mussels, we didn't find good information for many of the indicators. So it's also an important tool actually for finding knowledge gaps. Another way of presenting these results is that you focus on one theme. So if you focus on the environmental indicators, for example, looking at energy balance, GHG emission savings, and the colors represent the 3rd dimension, which is the local regional environmental impact, you can see that 4 of the feedstocks do quite okay, while blue mussel seems to have a very bad energy balance, and that also means like that you can't save much GHG emissions. As I said, we also looked at buses or coaches and trucks, and there are many alternative energy carriers, both fossil-based and renewable. We developed a method based on literature and in cooperation with stakeholders and experts. It had 4 key areas: technical, economic, and environmental and social performance, and 12 indicators. And this time, the results are presented as a spider diagram. It's just schematic, a few results, they are generalized. And we can start by looking at diesel. And the idea here is that very poor is a 1, and very good, then you're on the 5th level here. So a great advantage with diesel-driven buses or coaches is that they are very technical mature. Regarding energy supply, I just put it in the middle here, because if you're in Sweden, we have no oil extraction, for example, you would be down here. If you're in Norway, maybe you would be up here. So they can be very context specific, many of them. But then we can add another alternative, electric buses, fossil-based electricity, and then we see that they are less technologically mature, and where we can gain something in comparison with diesel is that we can avoid some inner city air pollution, and that they can be silent. But note that this is in inner city areas where you are driving slowly. If the speed is about 50 kilometers per hour, it's not the engine that's important. Then other type of noise sources are more important. So then it doesn't matter what engine you have. We can have another alternative. Biomethane from maize could look like this. So then, for example, we can improve regarding GHG emissions. We can avoid some inner city pollution. They can improve the noise levels in comparison with fossil diesel, but the electric alternative can be better here. And maize can commonly be produced locally, regionally, so the energy security is improved. We can have electricity from wind instead, and this could mean that we improve the GHG emission savings further. We avoid even more city air pollution since we have no power plants close to our city or whatever. Also really good regarding noise reduction, and you can commonly have wind power plants locally. And finally, I put in biomethane from manure, where you can, as previous speaker said, have even negative GHG emissions. They can be good regarding pollution and noise, like maize. But here you have local environmental benefits that are not that evident for some of the other examples. So the idea here is not to focus on these results specifically. The idea is rather to point out that it's very important how you conduct your studies, and if you make broad studies, you see these differences. And if you make a very narrow study focusing on tailpipe or only GHG, you miss a lot. And even if this looks broad, you should note that these are just a share of the indicators. There are more indicators, so the picture could have become even more complex. Right, so we are facing broad challenges. These are the planetary boundaries concepts, or we want to achieve broad goals. And then it's very advantageous if you have multifunctional solutions like Biogas Solutions. And if we move back to the previous figure and we focus on, for example, electric vehicles versus biomethane-driven vehicles, to me, some EU policy, for example, is a bit strange. Because compared to diesel, you can really gain if you are focusing on making inner city areas better with less noise and reduced city air pollution. But for example, biomethane-driven, at least heavy-duty vehicles can also contribute here. But if the electricity is fossil-based, you miss all the other parts here that you can get from a good biomethane, so a biogas solution, for example. Finally, another example. In Sweden, we have 16 national environmental objectives. Together, there are 71, I think, indices for following up. And a colleague of mine, Axel Lindfors, did a great work, and he checked what of these indicators, which of these indicators that were linked to the choice of energy carrier or fuel. And then some of them were overlapping, so he merged them. So we ended up with 8 indicators. You don't see them all here. Once again, it's a reduced picture. Diesel was put as the reference fuel. That's why it looks a bit different, strange here maybe. Some effects are not negligible, but if you really compare with diesel, there's no difference. But the main message here is if you, for example, want to address a broad environmental objectives, once again, Biogas Solutions can really support this since they commonly come with a broad range of positive sustainability effects. So takeaways from Biogas Solutions, for Biogas Solutions and the studies that we have carried out within this center based on multi-criteria analysis and other types of system studies is that since they are commonly multifunctional, you need a broad sustainability assessment method to consider the relevant values or effects. And if you generalize a little bit, at least if you focused on the waste-based biogas solutions, I would say the broader assessment, the better biogas solutions come out. And they can contribute to a wide range of societal benefits, like I emphasized before. But of course, it should also be emphasized that the sustainability performance is very context specific. But that's the case also for electricity, hydrogen, and fossil fuels. And biogas solutions can be critical and strategic components in a future more bio-based and circular economy. I also added 2 slides that I won't talk about. They are too detailed, but in the report Jerry mentioned, we have a summary of the sustainability performance of biomethane for transport, mainly contrasted to electric vehicles. So here you get general information and regarding some interesting areas. And I also have a slide with the references mentioned in the presentation. Thank you very much for the attention and for this opportunity.
Yeah, thank you very much, Jonas, for this interesting view on multi-criteria analysis. I hope we have the chance also to answer some of the questions from the Q&A. And again, feel free to add here. Some of the questions are already answered, but we will, of course, address some of the topics again in the panel discussion. But now we would like to see the last but not least presentation in this webinar here. The main idea behind the assessment of policy measures is that just wanting an implementation of biogas does not necessarily lead to an effective implementation. So it requires incentives, it requires policy measures. And we have a lot of examples where it didn't work or it went in the wrong direction. So doing this well is really a challenging task, and we are looking forward to the presentation of Marcus Gustafsson. He is also from the Swedish Biogas Solutions Research Center and also affiliated with the Linköping University. And Marcus, we are looking forward to your presentation.
Thank you very much, Jan, for that kind introduction, and also Jonas introduced me a little bit and what I'm going to talk about and what I do. So my name is Marcus Gustafsson, a colleague of Jonas at Linköping University and Biogas Solutions Research Center. So I'm briefly going to introduce the policy landscape for biogas solutions. I'm going to talk about policy measures and how they can affect biogas development. And I'm going to propose some recommendations for policy design. But first, I'm going to repeat a little bit what Jonas said about multifunctionality of biogas solutions, because that is important also when we look at the policy landscape. The fact that biogas solutions are multifunctional and often cross-sectoral, kind of like a multi-tool or a multi-athlete or a platypus. So that makes them difficult to define, and it's difficult to compare them to other systems or other functions, because other systems don't cover all of the functions that biogas solutions do. So because of the multifunctionality and cross-sectoral nature, biogas solutions are typically influenced by policies within many different sectors, because they are not only an energy production method, it's not only a question of environmental impact. It can also be waste management and wastewater treatment, agricultural issues and use of digestate. It can be a transport fuel, subsidies and taxes and different types of funding are important, and also building permits for constructing production facilities and infrastructure. So all of these sectors can have an influence on biogas solutions in different ways. And all of these policies can also address different parts of the biogas value chain, often in relation to the different focus and strategies in different countries. For example, if there's a focus on biogas in the agricultural sector and sustainable agriculture, policies are more likely to focus on anaerobic digestion and use of biofertilizers. Whereas if the focus is on biogas as an energy carrier, the policies will be more focused on the use of biogas and production of energy from biogas. Another very important dimension of biogas policies is the time, or how policies change over time. Because even if a policy framework is good right now, it may not lead to anything if the market cannot expect it to stay that way. And policies typically do change over time or exist for a limited period. And even in cases where they remain the same, like policy E, as the example in this figure, recurrent policy that stays the same, you want to be sure that it will not suddenly change from here to here from an investor's perspective. So if you're going to invest in biogas production, you would want the policy to be like A, in this example, that you can foresee that is a stable framework that will remain. One of the challenges with biogas production, biogas solutions, is that the production costs often are higher than what you can gain from selling the energy, especially if you have a small scale production. And there are different ways, of course, of compensating this from the policy side. Feed-in tariffs have been very common in European countries, where you have a fixed rate per kilowatt hour or megajoule biogas or electricity that is produced, which is often treated between state and biogas producers in the form of a contract or a purchase agreement. Feed-in premiums are getting more common, which is instead an additional fee on top of the selling price. And an alternative to subsidizing production is subsidizing the use through a tax exemption. That, of course, implies that you have a tax for fossil energy alternative. Then there are different ways of giving out premiums such as auctions, which they have, for example, in Germany since a couple of years, where biogas producers bid for how much support they require, and the lowest bidder, of course, would win. And so you benefit from being more efficient. Green certificates is like something you trade between biogas producers and customers to ascertain the green value of the gas. And then there's, of course, investment support for building new facilities or investing in gas vehicles, and also important methane reduction support, especially for reducing methane emissions from manure, which is commonly used in many European countries. So it's just a quick overview. I'm not going to go through this table, but it's just a sample of some European countries and what the policy for biogas looks like. So you can see there are some differences in economic instruments and regulations, value chain focus, and the time that economic support can be guaranteed. So you can read more about that in this article if you want later. I'll just dive into a few of these a little deeper to take a look at the effects that the policies can have on the biogas production development. And if we start with Germany and look at the last 20 years, Germany introduced a policy framework for renewable energy in 2000, including a feed-in tariff for electricity, renewable electricity, which laid the foundation for a dramatic expansion later on here of the biogas sector, mainly based on energy crops and maize in this case. And this system has been revised a couple of times over the years. Notably in 2014, they put a cap on the total biogas production in Germany. They wanted to promote solar power and wind power and other more economically feasible energy production systems, not considering all the other benefits from biogas, but more efficient energy production. So they put a cap on the biogas production and also cut the subsidies to large biogas plants. Only the smaller biogas plants could get the feed-in tariff. In 2017, switched from the feed-in tariff system to a tender system, the auctions, but the existing feed-in tariff contracts were still valid for up to 20 years from when they were signed. And from the last year, they have a special tender system for large biogas plants, which are then required to be flexible to produce either biomethane or combined heat and power. So the effects here were initially very positive, but when the system was changed, it has stagnated a bit. Move on to France, where they introduced feed-in tariff system shortly after Germany, 2001. And around 2005, they introduced subsidies for waste management, including anaerobic digestion, which you could say has given a bit of a different trajectory to the development compared to the German case, with less energy crops and more organic waste, so more focus on waste and circularity, and more on the agricultural sector. But both Germany and France introduced a cap for use of energy crops a couple of years ago. Then around 2009, there was a policy framework similar to the one in Germany, which was introduced in 2000, which in 2011 shifted focus a bit from heat and electricity to biomethane for grid injection, which you could say has been more successful as larger share of biomethane in the grid. There have also been goals issued to produce 70 terawatt hours of biogas and biomethane, and to have a completely fossil-free gas grid. We can also note that the majority of the new biomethane plants in the EU are built in France. So they're really going for biomethane production and grid injection. 151 new plants in 2021 and over 100 this year, while the rest of Europe in total has there's been built around 50 new biomethane plants. So they're hugely leading that development. Moving on to Sweden, where, as Jonas explained previously, the biogas development has been centered on waste management, upgrading to biomethane and use in vehicles. And this has been made possible mainly through economic incentive, which is tax exemption, energy tax exemption for renewable energy, which we've had for a long time. And in the beginning of 2000s, we also had an investment support for renewable energy production, such as biogas. In 2006, there was also a tax exemption for CO2 tax, because the fossil energy was laid on with a CO2 tax, but not the renewable, and investment support for gas vehicles. We had a manure digestion premium to treat manure through anaerobic digestion since 2015, and since last year it was introduced a production premium for upgrading and liquefaction of biomethane. So it remains to see if that can lift the development, which has been a bit stagnant in the last few years. And I will get to why I think that is. Because the next country I'm going to talk about is Denmark, which is not only a neighbor of Sweden, but there are also some interesting synergy effects on the policy side. So Denmark had a feed-in tariff for renewable electricity since 2004 or 5, which was increased in 2012, and that had very positive impact on the development, you could say. It also increases investment support and introduced a feed-in premium for renewable gas. So feed-in premium for biomethane to the gas grid, basically. And the aim here has been to improve the waste handling, especially in the agricultural sector, and to they have goals to recycle 50% of the household waste and to use 50% of the manure in aerobic digestion within 10 years from this point. In 2018, the feed-in tariff system was removed, but they still had a feed-in premium for biomethane, so it's still really going up here. And as I mentioned, there are some interesting synergy effects between Denmark and Sweden because of this feed-in premium that the Danish biogas producers get. They can sell their biogas to a competitive price through the gas grid connected to Sweden. And the users in Sweden also get the tax exemption. So it's a win-win from the perspective of the Danish biogas producers and Swedish biogas users. But the production in Sweden, as you could see, has not increased so much as the use. So this is an interesting case of how trade and policies in different countries can influence each other. Going to round off soon. Just want to give some recommendations, and the first recommendation is to look at the Gas for Climate report about national biomethane strategies. So it's basically a 10-step guide for how to develop a national biomethane strategy. You can also read an article that I and Stefan wrote about scenarios for developing the biogas sector in Sweden, which comes to more or less the same conclusions about which factors are important for developing the sector. So finally, the important things to develop sustainable and positive biogas policies is to have, first of all, long-term conditions, foreseeable conditions that investors can rely on and expect the value back for their money. Secondly, recognizing the whole value chain and not only the biogas as a product, but also biofertilizers and bio CO2. Not necessarily funding all of the parts in the value chain, but having a consistent framework. Regarding international trade, ensure that the green value can be preserved through guarantees of origin or green certificates, and preferably having harmonizing systems between countries and harmonizing gas standards. Many projects now and historically have been upheld by complicated and slow permitting processes. So that is something that needs to be addressed, I think. Finally, a coherent and consistent policy framework founded in a clear vision and a strategy. Yeah, so thank you very much for listening, and if you're interested in reading more, I posted a list of the literature here also.
Thank you very much, Gustav, for this, Marcus, Marcus, for this interesting presentation. And I would like just to say that we will upload the presentations on the website of this webinar, because there have been a lot of questions if these slides will be available, so they will be. And now I would like to continue to the panel discussion. We have some more participants here. We have Stefan Anderberg, we have Mats Eklund, and we have Kari-Ann Lück. I would like to ask you all to switch on the video now. And since Marcus and Jerry and Jonas had been already given the chance to introduce themselves, then I would like to ask you now, Stefan, Kari-Ann, and Mats, to just quickly introduce yourself and maybe give a short statement on the case, what we are discussing here today. Maybe Kari-Ann will start. She's the only woman in this round here.
Thank you, Jan. Yeah, so my name is Kari-Ann Ling, and I'm a researcher at the Norwegian Institute for Sustainability Research. And I work mainly with life cycle assessment, but also with biogas systems in a broader perspective. And I think all of the presentations today, they show that biogas systems are very complex, but also that the complexity is the strength of a biogas system. So it's really important that we, even though it's really complicated, that we keep doing broad assessments to show the positive effects of the different functions in the system. So I think all of the presentations were really nice, and there are very interesting discussions going on in the chat.
Okay, then Stefan, maybe you will be next.
Yes, I'm a professor of industrial ecology at Linköping University and a close colleague of Jonas, Marcus, and Mats in the Biogas Solutions Research Center, where I, together with Marcus, has tried to understand the policy landscape, and what I have besides what we have presented is an interest for the development of biogas on the EU policy scene, where it has long been invisible, but now things are starting to happen with the Green Deal and well, latest with Repower EU. So it's a much more dynamic development, but one is a bit worried about the policy developments because as Jan already pointed out, Biogas Solutions, it's a system improver often, and there is quite a diversity of biogas solutions, and it's not obvious which is the appropriate in a particular context, and it's a bit tricky to regulate such a thing, if we call it that. I think that the great challenge is to find some sort of balance with between encouraging biogas solutions and allowing a diversity of solutions. That's just a teaser for what I like to discuss.
Okay, thank you very much. I can't see Mats. Is he still here or not?
Has he been lost?
Okay, then I think I've taken some questions from the Q&A area. which I found might be interesting to discuss further here in this round. And there was one question which I also have not really a clear answer to. That's why I'm asking you. Maybe, I don't know, Jonas or Stefan can answer that. This is the question if it's better to have biogas application in large scale or rather in local small scale applications. I've seen also that EBA is discussing cost reduction due to economy of scale, which would mean, I think, also larger plants. But we all know that the substrates are available in a limited amount also on the site. So you rather have to transport them to a central place and then set up a large plant, or moving to smaller scale with higher costs and also maybe more problems to operate these plants. So what do you think is the way to go between these two different strategies?
Well,
I can maybe have a very short answer, and then I can hand over to all of the others. I think it depends. Commonly, you can gain from the large scale, of course, especially if you have like a grid system nearby. Then you can really expand, but it also depends on what to do with the digestate and so on. So I guess we will have a mix for a long time, and even if we have like an idea of what's rational, it's not really that's commonly implemented. For example, the farmers might have an idea of what they want to do, which is not directly related to what we find rational.
Well, that's one of the aspects where we need to allow both. I think that we need some larger plants. But we shouldn't throw out the small ones, and you can see many improvements in, you could say, the really local small-scale biogas production. And if there is a nice fit, it should be allowed to exist. And I hope that you will have a dynamic development also with the small scale biogas solutions.
Yeah,
but maybe it's a bit tricky, that one. In the latest Swedish biogas committee, they wanted, well, to have advice if they should have a lower limit for allowing support. But I think that would be unfortunate.
Yeah, we also have in Germany the tendency that the manure-based plants are smaller plants, simply due to the structure of animal husbandry. And of course, you want to have the manure in the utilization pathway, so that's why we support smaller plants. But then you won't have the upgrading for biomethane, and so this is, as said, really a complex decision. But I agree. It really depends on the substrate. It depends on your strategy, and both have their advantages. And for both, there should be room and strategy. So Mats, now we see that you are back. Maybe you just introduce yourself in a few sentences. And
sure, I can do that. I'm sorry, I had some technical problems and was thrown out of the meeting. My name is Mats Eklund. I'm a professor and also the founder of the National Competence Center in Biogas in Sweden. I missed out on a bit of discussions. I'm not really sure where you would like me to continue, but I'm open to any suggestions, Jan, if there is anything you want me to try to highlight or anything.
Yeah, we just had a discussion about what if there is a clear preference for small scale or large scale plants, but I would like to move on, and maybe the next question I would like to ask Karian. There was a question in the chat if there's any review of sustainability on biogas in the current market. And I think there are many aspects of that, but I think you are, since you are doing life cycle assessments and you are dealing with these questions, you might answer this question.
Yeah, so I think there are many different studies on the role of biogas in terms of sustainability. I know that the Swedish the Biogas Research Center has done a lot in that area. But I also think it's worth mentioning that biogas value chains, they are very different from country to country, and also the energy systems and the transport systems and the agricultural systems. So when you are doing a sustainability assessment, I think it's very much dependent on where the biogas system is located and the resources that are available and the energy consumed in the area nearby. So I think there's a need for doing regional assessments in this case. But of course, sometimes you can do more overarching studies that generalize a little bit. For instance, we've done, going back to the study or the discussion about the small or large scale, I think in Norway, we have kind of concluded that if we want to upgrade biogas to fuel quality and use biogas in the transport sector, we need the large scale. But on the other hand, right now, energy security is also an issue, which is also related to sustainability. So there are so many different aspects that you can look at.
Yeah, thank you very much. Yeah, I also think that this is also in Germany. It's not only that you need a certificate. It's also there are conditions to access the incentives. They are sometimes also connected to some sustainability criteria. So it's not always quite clear what is what. So it's clear certification scheme would help, I think, in Germany, which is also not only for one sector, because there's now a different system for fuel. There's a different system for electricity. The EU is now putting some pressure on that. So maybe this will be aligned in the future. Mats, there's one question here on the quality of digestate. And since I know that Sweden has a very particular path and is looking really into waste materials, how is this handled, and what do you think, what certification and quality standards for digestate have an impact on the biogas industry?
I think that in Sweden, I think it's more or less an initiative from the industry itself to actually, together with different actors, develop a system which certifies the use of biofertilizer, and really trying to separate that from sewage system and sewage sludge and everything. So, and we always talk about the word biofertilizer. So it's about creating something which is a product, which is understood as something very different from sewage sludge. And that has been successful, I would say. And there is still not anyone making a lot of money on it, but there is still definitely demand from a lot of farmers, especially the organic farmers, and they are prepared to pay more because they have very few alternatives if they want to be successful. And I think there is a continuous work on the certification process, and I just think that it seems to have become established, and no one really questions that kind of biofertilizer. So it's a mature system, I would say, and it seems to be working in relation to the demand from the different actors.
Okay. So Jonas, referring to your presentation on the multi-criteria analysis, I have no idea about life cycle assessment. So when I watch this, I usually asking myself, okay, what factors are going in there? What is now considered there? What is influencing this? So now you're coming even with multi-criteria analysis, which makes the whole thing even more complex. So what do you think how this can be applied in practice? So how could this be used to compare technologies without making the whole thing not handleable anymore? You know, if it's getting too complex, and how can you compare a wind turbine with such a system to actually come to a decision? What do you think how this could be applied in practice?
Of course, I mean, they are used in many different contexts, and it's very much up to also how you choose to design such a method. If you would have hundreds of indicators and you wouldn't aggregate results, it's very tricky to understand what do the results show. So commonly you need to decide upon a reasonable number, like 15 indicators or so you're able to look at the results. But we have very different alternatives, I think, or examples. I mean, some are more like research projects for us to learn, and maybe they have stopped there a little bit, maybe for further development, while others have actually developed practical tools for public procurement. So they are actually supporting public organizations when they are procuring transport services and so on. So there are such examples also that are very like straightforward and you can use as a practitioner. But of course it is a challenge, but the other way to make a very simple assessment and just focus on one indicator or two, of course you can have maybe exact and even quantified answers, but you have reduced the problem, so maybe it's not even interesting anymore. Would be my point. It's better to be about right and learn a lot during the assessment process than to limit the problem to something that's less relevant. And the challenging we are facing, they are multidimensional. I mean, we are facing a lot of sustainability problems. So I don't think we have the time to deal with them one by one either. It's not efficient and it will take too long. But I guess we have other comments also. And if it relates to LCA, and so Marcus is also really an expert, but there might be other views here.
Yeah, maybe Marcus, you could. What Jonas said is that we have multifunctional, multi-criteria analysis, but if I see politics, I think it needs to be very one-dimensional to transport the message. So, what do you think from your analysis of the policy measures? What would be the best way to really get biogas industry going? I mean, we have now the REPowerEU plan, which has quite an ambitious target. So you have set what policy should do, but how do you get this implemented?
Yeah, it's a bit of a tricky question and quite context specific. But in general, I mean, it's important to have a consistent and coherent policy framework, which has not been the case. And from the EU support really the biogas development and remove barriers for it. If we take the EU situation as an example, there used to be support for using biogas in vehicles, but now all vehicles should be zero emission electric or fuel cell. So that use support is not really there anymore. And it's not clear what it should be used for, these 35 billion cubic meters. So a bit more coherent framework from that side, but also allowing the member states to use the biomethane in what suits their context.
If I think that well, we have a new situation where we perhaps do not have to think so much about price support, There is a market, and well, the products are quite competitive, both when it comes to fuel and to fertilizer. Particularly the biofertilizers are much more attractive with the current fertilizer prices. So maybe policy should focus on identifying and bottlenecks and try to get rid of them, and try to well, continue harmonization, like the certification schemes you were discussing, Jan.
And if I may also add another thing, is that I believe that it's important to have a narrative, a framing around the biogas solutions, making it easy for politicians and others to understand what is the role. I mean, what kind of problems do we actually solve by developing the biogas solutions, and how does it go about? And I think that's one of the success stories behind the Danish development. I think they have a very mature and coherent story about the role biogas solutions play in their society. I think I haven't seen any other country that is like better than the Danes in terms of creating that. And they've been also quite consistent now for quite some time as well. So I think maybe that goes back to us to keep on improving the understanding of the how to solve important societal challenges with biogas solutions. I think we can become even better there.
I like to use that as the final statement of the webinar, I would say. I was quite encouraging, and I think, yeah, Denmark is a very good example. So let's take them and look at and learn from successful developments. And but of course, learn also from mistakes made in other countries. You don't have to make them again. So I think we have a lot of development in different countries with different approaches, and it makes a lot of sense to evaluate them and look at them. We are over time a little bit. I got already the message that we should end now the webinar. I would like to thank all the presenters and the panelists for the presentations and the discussion. I would like to thank the audience for spending their time. I hope you learned something, you got something from here. And we are, of course, also, we would like to see your remarks or potential feedback from your side. So please contact us if you would like to get some more information on the topics we presented here. And we will put on the recordings of the webinar on the website, and you will see also the presentations there. So I wish you, yeah, in whatever time area you are now, a good day or good evening or a good night. And we hope we see you again in this webinar series of the IEA Bioenergy. Goodbye, and thank you all.